All right, so it turns out like almost everyone in the room, myself included, you're going to screw up when it comes to anything memory related if you haven't already. Seg faults are in your future, but hopefully there's tools via which you can detect these things and fix them proactively and not just use printf or debug 50 or rubber duck. We actually have another tool we can equip you with now that'll help you find some mistakes. So let me do this. Let me close copy.c. Let me open a program I wrote in advance called memory.c that doesn't do anything really interesting, but it's going to have two bugs in it. Notice that I've included standard.io.h, as always. I've also included standard lib.h, which is necessary now for anything related to malloc and or free and the like. Line 6. It's a little weird what I've done here, but this is like the manual way of asking for enough memory for an array. In week 2, how do we ask for memory for an array? You very simply say int x3, and that gives you an array called x of size 3. But if you do it manually now using malloc, what you have to do is use syntax like this. You call malloc, you ask for 3 things, times however big an int is. Now we know it's 4, so you could literally write 12 here, but this is more generic. So 3 times the size of an integer will give you 12 dynamically. And what does malloc return? The address of the first byte you get back. What do I want to put that? Well, I want to put it in a variable. Now the variable can't just be int x, because that's a number. It's not an address per se. If I want to store this address in a variable, I could call it x, I could call it p. But int star x just means that x is now the address of a chunk of memory. Specifically, a chunk of memory that's big enough, not for 1, but for 3 ints in total. All right, now I'm just sort of naively putting our old friends 72, 73, and 33 at the first, second, and third locations in memory. But perhaps based on week 2 or week 4, I'm clearly screwing up here in a couple of ways. Someone want to identify at least one bug. What did I do wrong? Yeah, like this is now, amateur stuff. Like I should be 0 indexing, not 1 indexing. So this has got to be 0, 1, 2 ultimately. And other bugs that are maybe more week 4 specific? Other bugs. It's more subtle, yeah. I'm not freeing the memory, right? So I'm not practicing what I'm preaching by freeing this memory. Now, suppose these are non-obvious. And honestly, after like an hour or 2 of this, like this shouldn't be obvious yet. It will be over time. How could I find these bugs with software as opposed to just staring at the thing or asking someone for help? Well, let me propose this. Let me first go ahead and run make memory to compile the program. And it seems to look fine. There's no syntax errors, at least. /memory, notice, seems to work fine, too. Now, this program doesn't do anything interesting. There's no printf or anything like that. But it didn't crash. There's no segmentation fault. But that doesn't mean there aren't bugs latent in the software. And this is true, sadly, of all of today's software, like Chrome and Microsoft Word and other programs surely have memory-related bugs that people at Google and Microsoft haven't yet found. But there are tools, at least to find the most obvious of those bugs. And we're going to introduce you now to a program called Valgrind. So Valgrind, it's a fairly fancy program, but we'll use it for very simple ways. We'll look at your code and find memory errors as it's executing and try to help you understand where they are. So let me go back to VS Code here. Memory seems to be fine. I feel like, OK, I'm going to submit this homework. All is good. No error messages. That's no longer the case. Now you need to poke a little more at your code to see if maybe there's still some bug there. So let me do this. Valgrind. And then space /memory. So just like debug 50, you run it on a program you already compiled. Valgrind, I'm going to run it on a program I already compiled. Let me zoom in on my terminal window so we can see more at once, and enter. All right, the output is crazy cryptic for no good reason. There's lots of numbers and equal signs. It's a lot of clutter, but there is some juicy information here. And let me start from the top down. Invalid write of size 4. So write means to change a value. Read means to access a value. And this is, again, esoteric like a lot of our error messages are. But it looks like after a block of size 12 alloced, and then there's these weird hex notation. There's some mention of malloc. But honestly, the juicy part here is memory.c, line 6. That's probably my fault. So let's look at line 6 per that output. Let me shrink the terminal window. Look at line 6. OK, 12 is now germane, right? If you did the mental math of the size of an int times 3, 12 is somehow involved here. But line 6 is now happening next here. That's where the memory came from. What is this? Let me zoom back in. Where is there invalid write of size 4? Like, what's perhaps going wrong here? Invalid right of size 4. What does that mean? It's like a very technical way of explaining. The bug is actually one line later, on line 7, as we already identified. Yeah?
When you call x3, you are calling the fourth position of that integer. So I guess that doesn't match the memory you asked because you asked for
think through deductively, like, what could that mean? But I'm clearly touching 4 bytes of memory in these few lines of code that I shouldn't be. And hopefully here, as the light bulb already went off earlier, oh, I'm not 0 indexing. OK, that must mean that x bracket 3, as you note, is just too far past the chunk of memory. So I'm invalidly writing to 4 bytes that I shouldn't be. So again, it's not super obvious. This is not super user-friendly. But at least it does give you a clue as to where that bug is. So the fix there is going to be quite simply to change the 1 to a 0, the 2 to a 1, and the 3 to a 2. That'll fix that. But there's still a second error. And let me look at the cryptic output again. Heap summary, some stuff there. OK, this does not sound good down here. 12 bytes in 1 blocks are definitely lost in loss record 1 of 1. Very arcane output 2, but clearly related to line 6 again, our allocation of memory. Now here too, it's not obvious what the solution is, but memory is lost, aka this is a memory leak. And now the deduction's kind of up to you. What is leaking? Oh, wait, I didn't call free. And so the second solution here is probably to free x at the very end of the program. And if you really want to be pedantic, you should probably check, like I proposed earlier, if x is null, just get out now while you still can, and don't even touch those other lines of code. But if you get to the bottom, return 0. But really, the takeaways are, I fixed my 0 indexing of the array to avoid the invalid right of size 4. And now I'm freeing the memory that I asked for. So there should be no leak lost. All right, let's try this again. Make memory, /memory. No visible errors yet. But let me now increase my terminal window again. Do Valgrind of /memory, crossing my fingers. And now all heap blocks were freed. No leaks are possible. I don't see any invalid writes. There's still a crazy amount of output. But none of it is erroneous. It's not bad. Now I've fixed my memory bugs. And so now my TA, my TF, they're not going to find them either, because at least Valgrind has proactively done that for me. Questions then on Valgrind? Generally, it's those 2 types of errors you might trip over. There's not too much else in the way of arcane output. Questions then on this? No? All right. Well, what else might be going on? So someone alluded to this earlier. What happens when you, for instance, forget the null terminator? Or you generally start poking around memory that you yourself didn't ask for, or looking at values you didn't put there? Well, let me go ahead and open this. Code of garbage.c, in honor of Oscar the Grouch here of sorts. And here is a simple program. If I hide my terminal window, that just does something kind of arbitrary. I first declare an array called scores. But I made it crazy big, like 1024. Like, that's a lot of integers, but so be it. And then I iterate over those integers, and I print each of those scores out. So I'm using week 2 syntax here. But based on this program, what have I clearly not done that I did do back in week 2? I've allocated the array. I'm printing the array, but. Yeah, I didn't initialize any values for that array. Back in week 2, we didn't do 1024. We did like 3, and I typed in like 3 test scores or something like that. Here, I'm allocating memory, even more than that, just because I really want to be dramatic with what I'm demonstrating. But I'm not initializing those values to anything. And so here it turns out in C, generally, if you do not initialize a variable, or you do not initialize an array with explicit values, there are going to be garbage values there, so to speak. Remnants of that memory having been used before, probably by some other function of yours, some library function, or something else while your program is running. Not a huge deal with a super small program like this, but for anything sizable, memory is going to be used and unused and used and unused. That is mallocked and freed again and again. There's going to be lots of garbage values in the computer's memory by default. So if I open my terminal window here, let me do make garbage. Let me zoom in on my terminal so we can see the output. When I run /garbage, theoretically, I should see 1,024 integers, but none of which have been initialized. Now, I'm going to get lucky with some of them. And it looks like, wow, OK, a lot of them are initialized to 0. And C does, in some contexts, initialize memory for you to 0, at least at the beginning, but not again and again typically. But if I start scrolling backwards in time at this array of size 1024, where did these values come from? So just random positive and negative numbers interspersed among the zeros? Well, that's because I'm literally poking around on a random 1,024 bytes of the computer's memory. Who knows what's there? So the lesson here is that garbage values are indeed this like term of art. It means that a variable that you might have defined, that you might have declared, if you don't give it an explicit value, who knows what's going to be there? And the lesson here is just don't do that. Always initialize variables to something, either yourself or prompting the human for it. Questions about garbage values. You'll see them sometimes if you print things you shouldn't or touch arrays beyond their boundaries. All right, so maybe to make this a little visual too, it turns out that a lot of things can go wrong, unfortunately, with pointers. And we've seen some of them. And here's another program that's a little contrived. It's very simple. And it just is about manipulating values. It doesn't do anything useful per se, except demonstrate some of today's concepts. So in main here, let me propose that we declare a pointer called x that's going to store eventually the address of an integer, apparently. Here's another one called y that's going to store the address of an integer as well. Here now, I'm allocating enough memory to fit one integer. Now, technically, it's 4. We know that. But size of int just gives me that answer dynamically. So it will work on all systems. And I'm going to store the address that malloc finds for me in x. Then I go to x and put the number 42 there. All right, y, it's the sort of meaning of life, the universe, and everything here. But star x, again, just means go to that address and put a value there. So y, I don't know, but it's just correct at this point. But what about this line here? Star y equals 13. Unlucky in this case. What's bad about this line here, star y? It's a combination now of today's primitives and that point here. Yeah? Yeah, we didn't ask the computer to allocate any space. So y was not initialized with an equal sign at any point to anything. And so what is inside y, so to speak? Like a garbage value. Maybe it's 0, which isn't bad because at least it's nice and simple. But maybe it's some crazy large positive number, some crazy large negative number. Either way, odds are if I go to this address or that address randomly with star y, bad things are going to happen. And so let me go ahead and propose, well, let's not do that. Let's actually do this instead. In line, the second to last line here, why don't I instead assign y equal to x? And we've done that before. And then I can go to y now and change what was a 42 to a 13. Again, why? This is just for educational sake. But for now, this does not crash because I only dereference y with star y after actually giving it a value, albeit a duplicate value, similar to our copy example earlier. So our friends at Stanford have put together a wonderful visual. It's about 2 minutes long. Allow me to dramatically dim the lights if we could and play with what happens with memory when you do bad things like this. I give you Binky from Stanford University.
Hey, Binky, wake up. It's time for pointer fun.
What's that? Learn about pointers? Oh, goody!
Well, to get started, I guess we're going to need a couple pointers.
OK, this code allocates 2 pointers which can point to integers.
OK, well, I see the 2 pointers, but they don't seem to be pointing to anything.
That's right. Initially, pointers don't point to anything. The things they point to are called pointees, and setting them up's a separate step.
Oh, right. I knew that. The pointees are separate. So how do you allocate a pointee?
OK, well, this code allocates a new integer pointee, and this part sets x to point to it.
Hey, that looks better. So make it do something.
OK, I'll dereference the pointer x to store the number 42 into its pointee. For this trick, I'll need my magic wand of dereferencing.
Your magic wand of dereferencing? That's great.
This is what the code looks like. I'll just set up the number and...
Hey, look, there it goes. So doing a dereference on x follows the arrow to access its pointee, in this case to store 42 in there. Hey, try using it to store the number 13 through the other pointer, y.
OK, I'll just go over here to y and get the number 13 set up, and then take the wand of dereferencing and just... Whoa!
Oh, hey, that didn't work. Say, Binky, I don't think dereferencing y is a good idea, because, setting up the pointee is a separate step, and I don't think we ever did it.
Good point.
Yeah, we allocated the pointer y, but we never set it to point to a pointee.
Very observant.
Hey, you're looking good there, Binky. Can you fix it so that y points to the same pointee as x?
Sure, I'll use my magic wand of...
Did we lose audio?
Is that going to be a problem like before?
No, this doesn't touch the pointees. It just changes one pointer to point to the same thing as another.
Oh, I see. Now y points to the same place as x. So wait, now y is fixed. It has a pointee. So you can try the wand of dereferencing again to send the 13 over.
Okay, here goes.
Hey, look at that. Now dereferencing works on y. And because the pointers are sharing that one pointee, they both see the 13.
Yeah, sharing, whatever. So are we going to switch places now?
Oh, look, we're out of time.
But
All right, so our thanks to Professor Nick Parlante of Stanford for spending a huge amount of time doing stop motion animation for that. But hopefully now you have a sense of what too can go wrong when you misuse memory in this way. But at the end of the day, we really only have these 4 new building blocks today, like the star operator, the ampersand operator, malloc, and free. And really with that and the underlying understanding of what your computer is doing underneath the hood, we have this way now to really manipulate things in memory, for better or for worse, and eventually we'll see how we can build things.